Good morning and welcome to episode number 28 of the ZOOMTOWN experiment. If you're here watching me today, you actually survived my very lengthy episode number 27. I would like to apologize for that. However, when I started filming, I didn't realize the amount of complexity that positional feedback how much complexity was involved in it until I started getting through it and realized, wow, there's a lot going on there with those encoders and how important they are. This one might be a long one as well. We're going to be talking about acceleration. So we need to cover several different topics, and these may be far more interesting just outside of acceleration or the ZOOMTOWN experiment. One, we're going to cover what acceleration is. We're going to cover a few of the formulas that are very important to it, working with acceleration mathematically. And then we're also going to take a dive into how to make the code efficient to perform these calculations. Now remember, our clock cycle that we're running on right now is the premise. Every 5 milliseconds, I do everything. So everything we add into this whole process starts eating up that 5 millisecond window. So I spent quite a bit of time optimizing the code that we'll be talking about. But we're first going to go through and get an understanding of acceleration, what's involved with it. It's not as bad as it often can be made out to be. And finally, we'll look at it in the code. So with that, let's get into this slideshow that I've got. This topic will be about acceleration. It has to do with velocity control. Mathematically, the math people like to present acceleration as some distance, in this case meters, per second squared. And early on, when I was messing around with motion control, that always just confused me. It never made sense because, in truth, in my mind, it's simply a rate of change over time. I'm going to increase velocity or decrease velocity by a certain amount over a certain period of time. So I guess mathematically you could say that's per second squared or whatever the case may be. But to me, it just always confused me. We have to also understand that in the terms of math and all this other fun stuff, they refer to acceleration and deceleration the same way. One is you're accelerating up, one is you're accelerating down. Mathematically, it's true, but in just simple communications, for me, it makes a lot more sense to talk about acceleration and deceleration as separate entities. Mathematically, basically, they're the same. Same thing as rate of change over time. We need to kind of work within very specific units when talking about velocity and rate of change and so forth. And for example, you get in your car, if you're in the United States, you're going to be driving X number of miles per hour. Well, that's a way bigger time segment, distance segment than our little ZOOMTOWN. Over in Europe, it's kilometers per hour, etc. We're dealing with inches per second, or if you want a metric equivalent, that would be 25 millimeters per second. So that is our velocity, inches per second. Our rate is our change of inches per second every 5 milliseconds. And that 5 milliseconds is derived from our cycle time or our loop cycle time for the main loop of the program. So we will make a rate change or a change in velocity every 5 milliseconds. So it's a very short period of time. The distance that we're going to be working with will be inches. I'll try to do metric equivalents along the way as needed, but for the most part, this will be in inches per second. Now let's take a look at a somewhat similar example in that we're going to talk about acceleration, deceleration, and the very simple math to do that. But it all starts with understanding what rate of change you want per every time unit. The exact amount right now in the program for the Zoomy is 0.09 inches per second every 5 milliseconds. Now, if you take 1 divided by 5 milliseconds, you will get 200. That would be the number of cycles to get all the way up for a full second. So in 1 second, if I take 0.09 times 200, I will get 18 inches per second. So it takes 1 second to get up to that velocity. Our maximum velocity is 9 inches per second. So in a half a second, then, I should be able to achieve full velocity. So far, that's actually been working quite well in a practical sense. Now, acceleration, the math for that is you take your current velocity and add your rate of change, your amount of change, 0.09. And then deceleration would be the current velocity minus the rate, or minus 0.09. And you do that, in our case, every 5 milliseconds. Now, every motion will include 3 phases. Now, that's a little bit of a misconception there, but for the purposes of this explanation, we're always going to assume we're starting at some velocity. We need to achieve a velocity, and we will decelerate to another velocity. Now, that starting point, and in the case of this motion, ending point, it may or may not be 0 inches per second. In fact, we will, in the practice, we'll actually be stopping at a value a little bit more than 0. But the 3 phases are always acceleration, I call it cruise speed for our duration of the motion, and then deceleration. Now, during acceleration, all we're really doing is every 5 milliseconds, we're going to be adding to the velocity our rate of change. And in our case, in the example thus far, it's been 0.09 inches per second. And that's what's used in our Zoomy's program as it exists. And we will repeat that until the desired velocity is achieved. And I call that desired velocity the cruise speed. Likewise, when we want to decelerate, we would decrease the amount of velocity by that rate of change. So we would subtract the 0.09 inches per second every 5 milliseconds. Now, the thing that you'll probably need to know right away is we can accelerate up to our velocity. Okay, that essentially we don't really need to know how long that'll take per se. However, in order to decelerate, we have to know in advance when to start decelerating. And that's where the math gets a little bit more complicated, but with our simple approach to the acceleration and deceleration, it's really not that difficult, but it is a series of steps to get the end result. Now, here are the calculations that we're going to be using in the program. And I wanted to break it out this way because by the time we get into the code, it's harder to interpret because this is all condensed down into one line of code. But we need to start out by getting the amount of change in velocity we want to cause. So we would take our start velocity minus our end velocity. In this case, we're decelerating. We need to figure out how many iterations, how many clock cycles that's going to take. So we would take our delta change divided by our rate of change. So in this case, it would be roughly 1 divided by 0.09 in our previous example, but we'll have different numbers coming up shortly. We need to know the time it takes to change, and that would be computed by taking the iterations times the rate of change. We will also need to know what the average velocity is. That's handy for a couple of other things along the way. And to get that, we would take our delta change divided by 2 plus the end velocity. And finally, we need to know the distance to decelerate. So we would take our decel time, our deceleration time, times the average velocity. That's why that's so important. Now let's look at an example with real numbers, and this will play into our little side video coming up here very shortly. Now the calculations in this case will be used with real values. We're going to have our velocity, starting velocity is 3 inches per second, end velocity is 2 inches per second, so we're only slowing down a little bit, or 1/3. Our rate of change for this example is 0.1. And the interval, our clock cycle time, is 0.005 seconds, or 5 milliseconds. So let's look at how the math works out here. We want to get our delta change, and that is achieved by taking start velocity minus end velocity, or 3.0 minus 2.0, and that gives us 1 inch per second. The number of iterations for this to happen, I would take the delta divided by the rate. And that would be 1 divided by 0.1, meaning 10 loops. Our decel time, we would take the number of iterations times the interval, in our case 0.005, so that would be 10 times 0.005, and that gives us 0.05 seconds, or 50 milliseconds. Our average velocity is the delta change divided by 2 plus the ending velocity. Remember, this is deceleration. So that would be 1 divided by 2 plus 2.0, the ending velocity, and that gives us an average of 2.5 inches per second. Finally, for the distance to decelerate, we would say decel time times the average velocity. So 0.05 times our average velocity is 2.5 inches per minute, and that gives us 0.125 inches of distance to decelerate. You may want to go over that code a few times, and then it'll start to make sense. I don't think there's a more efficient way to get all the data that I want, so I think it's pretty well refined at this point, but believe me, I'm wide open if somebody's got a better, faster way and they want to comment about it on the YouTube channel. Now we're looking at the actual code. Acceleration distance equals run velocity minus minimum divided by the acceleration rate times the number of milliseconds for each clock cycle times the run velocity minus the minimum velocity divided by 2 plus the minimum velocity. And all that is what we just covered. And you, like me, probably look at that and go, oh boy, that's hard to interpret and read. It is. I generally don't like long formulas like that. I'm too ADD. I'll get lost halfway through reading it half the time. But that's where you have to make compromises between efficiency and ease of use, or in this case, ease of reading it. And that will bring us to a little side story here. And this is one where if you're interested into optimizing code, this is kind of an interesting example of it, because I started out very procedural, like I presented with that slideshow a minute ago. And I created this little test program, and I'll include this in the packet of data. And basically what I'm talking about up here is comparing procedural versus combining everything into a single line formula. Now, depending on who you listen to and how things are communicated, some people will tell you that calling a function just wastes way too much time. I haven't really seen proof of that consistently. Some people will tell you that having a procedural line-by-line formula over multi-lines is faster. I never really believed that, because I just figured there's a whole lot more clockwork, a whole lot more going on to get from one line to the next line to the next line. and you're writing data to local variables to carry over from one to the other. So I just thought it would be important that we look at this from a real point of view, a practical point of view. So what I've done was to look at how much time I can save by taking a procedural formula line by line, condensing it into one line. And as I discovered, the cycle time was reduced by 65%. That's very substantial. Was it worth it to get a reduction of 65% at the cost of making the formula less readable? That's to be debated, but I could have described that same formula in comments so that it could make it understandable and then not really suffer when we're looking at the single line. Okay, now let's move through the code. I'm just importing a library, setting a few variables that we need. These will look familiar to what we've already discussed. I have a function here called distance to decelerate and one called distance to accelerate. The biggest difference between the two is this one is doing everything procedural. This one is all on one line. So that's what we covered. This is how to make it all on one line. And like you, I think this is more readable. I'm going to reset the variables. And then, let's see. Got that. Okay. Here I'm going to reset some variable data. We will start a cycle time here. So this will run first. It will go through, do all these calculations, and then we'll print out the time. And this will be procedural within the main program. And I'm just saying distance to decel and distance, etc. The important thing will be how much time it takes to do that. Then we're going to do that again, but this time we're going to call it in a function, calling procedural function distance to decel. Now we're going to do an acceleration using the same data, calling from a function, calling one line, or I'm calling a single line version of the formula in a function. And then finally right here, we'll do the same thing inline in code. Now the reason why I'm doing it in a function and doing it inline to see what the time difference is. And then of course, the same thing being procedural inline or procedural in a function. Which is fastest? Let's find out. So I'm just going to go ahead and run this. I'll clear out this down below here. We'll run it. And this is what we're going to get. Procedural within the main program took 240 microseconds. And one thing I should point out, here are all the same end results from each formula. Now, if I'm calling procedural function, notice that it's 171 microseconds. This is inline code, this is in a function, and it's quite a bit faster. That was a surprise to me. Then we'll go to the next phase of this. We're calling a function to do the one-line statement. That took 87 microseconds. When it's inline, it takes 92 seconds. Isn't that fascinating? So I didn't really know how to interpret why inline is slower than running from a function. And I'm sure somebody has an idea on that, or a suggestion or a comment, but I couldn't rationalize it. I did rationalize this. There is a huge improvement to go from running procedural versus one line. And to me, that was of great value. In reality, it's only about 90.09 milliseconds. Doesn't seem like much, but when you're really trying to squeeze as much out of something, that adds up to big money to me. Now, somebody might say, well, that's because of the first time. I also ran this multiple times. Now, this isn't a fair test, but I'm getting very consistent results there. If I put it in a loop and ran it, I'm sure the results would change. But I hope you understand and maybe even appreciate the importance of taking some time like this every once in a while to try to refine your algorithms, your formulas, your procedures to get them as efficiently as possible. For me, they paid off big dividends here that are going to be very important as we get a little further along with the full Zoomy program. Before I go through the rest of the code, I just want to show you what it looks like for our Zoomy to move along with acceleration and deceleration. And then we'll look at how this is handled in the code. Before we go diving into the code, we'll go ahead and run an example here on the bench with the actual Zoomy. We're going to move forward a total of 17 inches. Now at this point, the velocity is currently set to 5 inches per second. So it's a rather slow movement. But let's see what that looks like with a nice smooth acceleration and then deceleration. Again, we're going 17 inches. It went exactly 17 inches. Well, if we look at my error here, my total error is about 6 thousandths of an inch. That would be 2 thicknesses of a piece of paper. That's my positional feedback helping me out there. And it also goes to show how accurately it is with starting the deceleration and ending at our destination point. Now let's take that up. I think I can go to 9 inches per second. So let's see what the behavior is on that. Take a second to run through here. Get downloaded and in. And again, nice smooth operation. Accelerates up to velocity, gets to its start point, decelerates back down to 0. So it works very good. That time we saw a total error of 17 thousandths of an inch, less than a half a millimeter. And probably some of that is in backlash in the gearing, as we were probably coasting faster than the motor really wanted to go. So that gives you an idea of what we're looking at and how all of this has a practical effect at the output end of it, meaning the Zoomy moving. So let's go through the code. We're going to start kind of at the bottom so that you get an idea of how we deal with this running at every 5 milliseconds. Now, if we go up here, forget these adjustments here, but here's handle velocity controls. I call the function auto adjust velocity, and then I record the time it took to perform that. And we actually already went through that in last week's episode, but if we go up to here, that takes a total of 0.237 milliseconds to perform all that activity. Now let's come down and see what is doing what. And I want to get past all this other code. Right here, we're going to just take a quick peek-see. We've got a max velocity and a min velocity. We already talked about those. That's the maximum I want the Zoomy to go and the minimum. We're going to need a number of variables that control velocity here. We will have a set velocity, a target velocity, a run velocity, an acceleration rate. There's that 0.09 we discussed earlier. An acceleration distance, I put that as a global because that needs to be accessed from multiple locations. Distance to go was a positional variable. And then system variable cycle start isn't really applicable here, but system variable override. This is currently set to 1, and that is the override control coming from the scheduler. That could override what we want in velocity by an amount anywhere between 60 and 100%, or all the way down to a full stop. This plays an important role in all of our calculations for velocity control. Now these two functions here we're going to bypass for now because they're kind of at the end of the adjust velocity process. So I'm going to just scroll by that, and we're going to go to this guy. Now this is the one that you see, or you saw down in the main loop, where we're calling that every 5 milliseconds. And I'm going to be reading a lot of the commentary here because that will help convey the way this was written. The routine adjusts velocity based on various needs and inputs, determines when to decelerate motion, checks CAS routine, as this affects velocity control, adjusts the velocity depending on system override, adjusts velocity if E-stop is active, adjusts velocity if it's going too fast or if too slow, adjusts velocity slower if too fast and faster if too slow. It will calculate the acceleration distance. It will adjust velocity for turns. It will adjust heading by applying a PID control to the velocity. This will be more for the steering, and we'll be covering that in an upcoming episode. And then call function to set the velocity for the motor driver, and that's those two functions above. Now, distance to go, if the distance to go is less than the acceleration distance, meaning the distance to decelerate, we will make that test and then set velocity to ending velocity for decel. So we're going to take our minimum velocity and assign it to set velocity. That's what we're, not necessarily our target, but that is the value that we're setting at as the desired velocity. We're going to check CAS. You don't even know what that is yet, so I'm just going to skip over that. And now we're going to take into account all of the stuff that affects our target velocity. Our set velocity, our system variable override, which would come from the scheduler computer, as will the E-stop, as will the CAS system. All three of those will modify the target value, but it's all based on the set velocity. Now, if the run velocity is less than the target velocity, that guy, we have to start at least at minimum velocity to get going, and that's so we don't spend a lot of time accelerating through the dead band. The dead band would be any PWM signal that's too low to cause the motor to start rotating. So we don't even waste time in there accelerating through that dead band. We just jump ahead and start accelerating at the minimum velocity. Here we add to our run velocity our acceleration rate. That's that simple math I was talking about. Now, if we went too far, we will make them equal. That way we don't exceed what we want. Otherwise, if the velocity is faster than desired, faster than our target, we will subtract our acceleration rate, and then if we went too low, we will make it equal to our target velocity. Not so bad, right? That part's pretty straightforward. This is the calculation for the acceleration distance for deceleration. Remember, in the world of physics and math and all that fun stuff, acceleration is the same as deceleration, but I need to keep track of it in my head. And this is the big full formula here. So we can, if you want to dig into that, you can break this down based on the examples in our other example program where we did all the timing. But that's just doing that calculation. This next area here, I don't want to go over this yet. This will be a separate video because it's taking into account effects of both position and velocity control. But it's dealing with how we'll be performing line following, as well as what I'm calling encoder steering. So we're just going to skip over all that for right now. But at this point, we've got our a velocity that we want to run at. And this is constantly changing. Remember that. So every 5 milliseconds this will happen. So we're going to call the routine set velocity, and we'll pass it in the left run velocity and the right run velocity. And why I have to pass in two when we're doing steering, which was this code, we need to have individual velocities for each wheel to cause it to turn. So now we go back to this set velocity, left run, right run. This is our final processing of the desired velocity setting. It converts IPS to duty cycle. And again, if CAS is not active, it will limit duty cycle values to a functional range. And this is all it really takes to calculate the duty cycle at this point. We need it to be an integer. Duty cycle is specified in integer. So I'm going to take the integer of left run velocity divided by the maximum velocity and then times the total or the max range for the duty cycle, which is 65,535. And I'll do the exact same thing for the right wheel. Now we don't yet know what CAS is. That'll be the subject of a future video. So now we can get down to this one. If our distance to go is less than the end of the move, we're going to force the duty cycle to 0, meaning we overshot. And same for the right wheel. If the right distance to go is less than 0, we overshot. Then we're going to call adjust run velocity, and we're passing in that in left duty cycle and right duty cycle. And that is this guy here, adjust left duty cycle, right duty cycle, and all we're doing is setting the motor controller duty cycle through the I2C interface so that it runs at the proper speed. And that is acceleration. Frankly, that's the bulk of it. It's all handled by these few routines. And as you saw, the math, other than predicting distance to decelerate, is quite straightforward. Now, there's another one here that you will see that it pops up in our code. It says adjust run velocity to 0, 0. In this case, I'm directly controlling the motor via the duty cycle. I'm telling it run at 0 duty cycle for both left and right, and then that way the motor stops. But again, this is the guy right here that's calling it every 5 milliseconds, so it's constantly adjusting. If the Zoomie's moving too slow, it'll force it to speed up. If it's going too fast, it'll force it to slow down. If it's not going straight, all of this plays into our velocity control functions. Now we'll give it one last example here to end out this video. I'll just run it again, same velocity, same everything as last time. Clear that out, and we'll give her one last run. And again, you'll notice that it went pretty darn straight, and our error on that movement was a total of 0.003 of an inch, the thickness of a piece of paper. Isn't that awesome? So all around, it's all starting to come together now. We've got the very important fundamental functions. We've got position feedback, so that we can control position. And we've got velocity control output and feedback from the position data to determine current velocities. Now from that we can construct all of the motions that the Zoomie needs to perform. So that's going to be a big part of our upcoming videos over the next few weeks. I do want to let you know that the next two will be focused around encoder steering and then line follow steering. And that in itself is an interesting topic, I think. Line following can be very basic, but encoder steering just kind of doing the same thing with two different types of input, right? Our photo sensors are telling us where to steer based on the color of a line beneath the car. That's the input. When we're doing encoder steering, I'm comparing the left encoder count to the right encoder count to adjust the velocity so that I drive in a straight line. So those will be some shorter, hopefully shorter videos, and I believe they're very interesting. Hopefully you guys will find them interesting as well. So this will wrap it up for this week's episode, and I look forward to seeing you next week.